Welcome back to Quantitative Chemistry, and in this video we're going to be doing similar calculations to the ones we did in the last video, which was reacting mass calculations. We're still working on 1.7.5 in the specification, but this time we're going to include examples where there is a limiting reactant. And essentially we're not doing anything different, we just have a couple of extra steps with these ones. So we're going to be starting on page 22. So we're on page 22 now, and we want to talk about this idea of limiting reactant and excess reactant. What your notes tell you here is that when we're doing a reaction, we rarely mix just the right proportion of reactants when we carry out a reaction. So if we look at this equation above, which we looked at in our last video, what we're saying with this equation is that we need to mix a ratio of 2 moles of magnesium with 1 mole of oxygen to give me 2 moles of magnesium oxide. That's our ratio as such that we need to mix our reactants in, and the ratio of the product that will be formed. So we need to mix our magnesium and oxygen in a ratio of 2 to 1 moles, but we rarely do that. We rarely say, for example, I have 4 moles of magnesium, then I use exactly 2 moles of oxygen because my ratio is 2 to 1. Quite often we will pick the more expensive reactant and use less of it. So for example, I might use 10 moles of magnesium, but actually use 50 moles of oxygen. So you can see in this equation, I've used far more oxygen than I need to. If I used it in the proper ratio, I would only be using 5 moles of oxygen, but instead I am using 50. So unless we mix our reactants in exactly the right proportion, there will always be what we call a limiting reactant and an excess reactant. So the limiting reactant is the reactant which essentially stops the reaction happening at some stage. It's the one that limits the reaction from going any further. Once it's all used up, then the reaction must stop, because once I have no more of it to react, I can't form any more product, even if there's some of the other reactant left, because it has nothing to react with. So in this equation above, once all the magnesium has been used up, the reaction can no longer continue. Yes, I might have an excess of oxygen, but the reaction cannot continue because I have no more magnesium left for it to react with. So that's the limiting reactant, the reactant that stops our reaction from going any further. Then we've got what we call the excess reactant, and that's the one where essentially we have excess of it, just as the name suggests. It's the one that remains when the reaction is complete. So for example, once we've used up our limiting reactant, there will always be a bit of the excess reactant left. The reaction can continue because there's no more of the limiting reactant, but I'll have some left over of the excess reactant. In the equation we looked at above, it was oxygen. We'll have some oxygen left over when the reaction is finished. Because once the limiting reactant has all been used up, there's nothing left for this excess reactant to react with, and so it can form no more product. And that's when the reaction finishes. So to demonstrate this idea, it can be helpful sometimes to use the analogy of a packed lunch. So your packed lunch will be made up of different components, and how many packed lunches you can make will depend on how many of the components that you have. You've got an example here in your notes, but what I thought I would do is demonstrate this for you as well. So to demonstrate this idea of limiting reactants, I'm going to make up some packed lunches. So the reaction as such is going to be making up the packed lunches, and my product as such is going to be the final packed lunch. What's my final packed lunch going to have in it? It's going to have a sandwich, a banana, and a Kit Kat. So to make one full packed lunch, I need a sandwich, a banana, and a Kit Kat. Okay, at the minute to start off with, I have 4 sandwiches, I have 5 bananas, and I have 3 Kit Kats. So let's see how many packed lunches I can make. So let's try and make one. So I've got a sandwich, I've got a banana, I've got a Kit Kat. There's one pack lunch. I've got a sandwich, a banana, and a Kit Kat. There's 2 pack lunches. I've got a sandwich, a banana, and a Kit Kat. That's 3 pack lunches. And I've got a sandwich, a banana, but I can't make a 4th pack lunch because I have no more Kit Kats. I've got a sandwich, I've got a banana, but my pack lunch can't be complete because I don't have any more Kit Kats. So in this example, in this reaction as such, my limiting reactant would be my Kit Kats, because I don't have enough Kit Kats to make another pack lunch. It is what is stopping the reaction from going any further. I've got enough sandwiches to make another pack lunch, I've got enough bananas to make another pack lunch, but I don't have enough Kit Kats to make another pack lunch, and so it is limiting me from going any further in my pack lunch making. It is the limiting reactant. But let's look at one more example, keeping up with pack lunches, because let's face it, we don't want to have the same pack lunch every day. What happens if we mix up our pack lunch? So I'm going to make up some more pack lunches now, except this time my pack lunch is going to have a can of baked beans, 2 oranges, a crunchy, and an apple. So I'm making up some more pack lunch, but it's got different components to it now. What I'm starting off with, my starting reactants as such, are 5 cans of baked beans, 7 oranges, 4 crunchies, and 5 apples. So let me repeat that. 5 baked beans, 7 oranges, 4 crunchies, and 5 apples. So which do you think is going to be the limiting reactant this time? Well, let's see how many pack lunches we can make up to determine our limiting reactant in this reaction. So I need 1 can of baked beans, 2 oranges, a crunchy, and an apple. There's 1 pack lunch. I need a can of baked beans, 2 oranges, a crunchy, and an apple. There's 2 pack lunches. I need a can of baked beans, 2 oranges, a crunchy, and an apple. There's 3 pack lunches. Let's see if I can make another one. I need a can of baked beans. I need 2 oranges. But I only have 1 orange left. So therefore, I cannot make another pack lunch. So in this case, our oranges are our limiting reactant. My oranges are what are stopping me from making another complete pack lunch, because I need 2 oranges to make the pack lunch. Yes, I've got 1 left, but that's not enough to make a pack lunch because I need 2 of them for 1 pack lunch. So you can see I'm left over with 2 cans of baked beans. I have enough baked beans to make another pack lunch. I have another crunchy, so that's enough to make another pack lunch. And I have 2 more apples, so that's enough to make another pack lunch. But my oranges are what are stopping me from making my final pack lunch. But let's think back to how many we had in the first place. We had 7 oranges. We only had 5 cans of baked beans. We only had 4 crunchies. And we had 5 apples. So actually we had more oranges than we had baked beans, crunchies, or apples. But they are my limiting reactant because I needed 2 of them for every pack lunch. And we'll come on to that later in our examples of actual chemistry examples, that we need to take into consideration the number of moles of reactants that we need to make products. We have to take that into consideration as well, because you may have guessed that crunchies were your limiting reactant because I've got the lowest number of them to start with, the lowest number of crunchies. But actually oranges were our limiting reactant, even though I've got more oranges than any other of my component of pack lunches, because I need 2 of them to make my product. Actually, they are my limiting reactant. So we have to take that into consideration as well. Okay, so let's move on from pack lunches, because let's face it, you won't get asked about pack lunches in your exam. You're going to get asked about actual chemical reactions and be asked to calculate values. So let's look through the steps that we need to take. And what you'll notice is that these are very similar to our reacting mass calculations. There's just a couple of extra steps. So first step is, just as we've done before, is to write all the information you've been given underneath the equation. And I'm going to highlight these in a few different colours, just the same as what we used in our reacting mass calculations, just to keep that consistent. So we're going to write down the masses that we have been given underneath our reactants. In this case, it will only be masses of reactants that you're given, will only ever be going left to right in this case, and we'll see that in a second. Also write down the RFM of the things that you'll be using, and a question mark underneath what you're going to be trying to working out. Number 2 then says calculate the number of moles you have of each of the reactants. So in this example, rather than just saying you have 20 grams of magnesium, you'll be told that you have, say, 20 grams of magnesium and 10 grams of oxygen. And so we're going to need to do at least 2 calculations here of how many moles of reactants that we have. And we'll see that in our example. The next step that we need to take is to divide through by the stoichiometry. In other words, the balancing number in front of that substance in the equation. And that will be for each of our reactants as well. And again, we'll see that a little bit more in our examples, but I'm highlighting that in blue. I'm going to do that in blue colour when we're doing our calculations, just so we see each one of the steps. Number 4 then is to determine which is the limiting reactant, and it will be the one that after you've divided through by the balancing number, it will have the lowest value of moles. So we'll have the lowest number of moles of it. So essentially once that amount of moles is used up, our reaction can't continue because that reactant has run out, and so our reaction finishes. And then finally, we use this value to bring over to the right-hand side. When we're transferring the number of moles, it's the limiting reactant that we use. And this is where we transfer our number of moles over with our arrow and consider our balancing number ratio. But I want you to put a little note. I'm going to do it in yellow because that's the colour we do our transfer in. And we certainly used that in our previous video. But we need to be careful, particularly with these examples, because think back to step number 3. Step number 3, we divided through by the balancing number. So if you remember when we were transferring our ratio, essentially you divide by the number in front of what we're moving from, and you multiply by the number in front of what we are going to. But in step 3, we've already divided by the number in front of what we're coming from. So we don't do that step again. So essentially when we're transferring moles, we simply multiply by the number in front of what we are going to. So I'm going to write a quick note about that. So if you want to maybe write that into your notes, we will see this better when we're doing our examples, but it's just to have that in your notes, that warning of being careful when you're transferring the moles. Remember that you have a balancing number, and then we've got to take that into consideration when we're transferring moles, but also that we've already divided in step 3. So really we're just going to multiply by the number in front of what we are going to, which will be our final stage of the calculation, working out how much product we will get from this particular reaction. Again, we'll see all of this better when we do a worked example, but it's making sure those steps are there in your notes. And remember to use these when you're doing your own calculations by yourself. Use these steps, make sure you follow it step by step, because if you miss out a step, you will lose marks because you will get the wrong answer. So it's worth taking your time and doing this step by step. So let's look at a worked example now, but please keep looking back to the steps. I'll be referring back to them anyway, but please keep referring back to those steps up at the top of the page. So let's see what we have here. So worked example 1 says, what mass of magnesium chloride is obtained when 25 grams of magnesium is combusted in 90 grams of chlorine gas? And you're given your RFM values as well. So remember, step number 1 is to write what we know underneath the relevant parts of the equation. So let's see what we have here. We've been told that we have 25 grams of magnesium. So let me write that underneath the equation first of all. So 25 grams of magnesium, I'm writing that underneath Mg, 25 grams. I've also been told that I have 90 grams of chlorine gas. So I write that underneath Cl2. So notice how this is different from our previous examples. We've been given the mass of 2 of our reactants. And what we need to do, like the packed lunches, is we need to work out what's going to be our limiting reactant, what's going to stop us from going any further. And that will determine the maximum mass of product that we can get. What's the thing that we're trying to work out then? The question asks us what mass of magnesium chloride is obtained. So what I'm going to do is put a question mark underneath MgCl2. So I know that that's where I'm going when I get to that stage of my calculation. What we also want to do is write down our RFM values below the relevant part of the equation. So you can see they've been given to us, so I simply need to write those in. The RFM of magnesium is 24, the RFM of chlorine is 71, and the RFM of magnesium chloride is 95. So I simply need to write those in. Step number 2 then is to calculate the number of moles you have of each of the reactants. So rather than just working out the number of moles I have of magnesium and then bringing that over, I can't do that. I need to work out how many moles I have of magnesium and how many moles I have of chlorine. So let's start with magnesium and we'll work it through. So when I'm calculating number of moles, remember your key equation. N for number of moles is equal to mass over RFM. Our mass of magnesium is 25 and our RFM is 24. Put that into your calculator now. So actually get practice in putting these into your calculator with me. That should come out as 1.0416 reoccurring. And so we can round that off to 1.042. Okay. What we are told in step number 3 is to divide through by our balancing number. So in front of our Mg, I have no balancing number. Essentially, the balancing number is 1. I'm sure you know that when you divide by 1, you just get the same number, but I'd like you to write this in anyway so that it's there as a step, because this is going to be really important in future examples. So at this stage, once you've worked out the number of moles of a reactant, always do it there and then so you remember. Divide through by the balancing number in front of that particular part of the equation. So there's essentially a 1 in front of the magnesium, so I'm dividing through by 1, which gets me the same number of moles. What we need to do now is do the same thing but for chlorine. So again, working out the number of moles using the equation N equals mass over RFM. This time my mass is 90, my RFM is 71. Okay, take a minute to put that into your calculator. Okay, and that should come out as 1.2676. What we need to remember to do at this stage is to divide through by the balancing number. Again, if I look in front of chlorine, there is no number, so essentially it's a balancing number of 1. But again, I'm going to write this into your notes so that you remember to do this step in each of your examples. So we're dividing by 1 and that's going to get us the same number of moles. So what I need to do now is step number 4, which is to determine which is the limiting reactant. The limiting reactant is the one in which I have the lowest number of moles, but this must be done after you divide through by that balancing number. Otherwise, like we saw with the packed lunch that we made up with the oranges, if you don't take into consideration the ratio of moles that you need of that reactant, then you could end up picking the wrong limiting reactant. So in this case, our lower number of moles is of magnesium. So I'm going to put my box around that, and I might even write underneath LR, limiting reactant. And that's the one I use to bring over to my magnesium chloride to determine the mass of the product that I form. I always choose the lower number of moles. So this is us on step number 5. And I'm going to draw my arrow over to my product. Now, at this stage, remember when we're transferring moles, we've got to take into consideration our balancing number ratio. You can see here that the ratio is 1 to 1. However, what you also need to remember is that you've already done the first step. You've already done the divided by 1 stage, essentially. It won't matter in this case because we're dividing by 1 and multiplying by 1, but it will matter in future examples. So rather than writing 1 to 1, what I'm going to write in this example is multiply by 1. Because if you think about it, we have a ratio here of 1 to 1, but what we did here was we divided by 1 already. That step is already done, so all I need to do is the multiplied by stage, and this will be important in future examples. So instead of writing 1 to 1, I'm just going to write times by 1. When we do these examples, we're essentially just going to multiply by the number in front of the product that we are going to, and we'll see that in future examples. So we're just multiplying by 1. That's going to give me the same number of moles. So that's 1.042 moles. Okay, think about what you're asked to calculate in the first place. The question asks you what mass of magnesium chloride is obtained. So to work out the mass, I use the equation mass equals N times RFM. And at this stage, it's exactly the same as our previous examples. We just fill in our number of moles, which was 1.042. We multiply by 95. And the exact answer you get will depend on how accurate you've kept your number. I stored my number from the first part of the calculation when we were calculating the number of moles of magnesium. So I'm using that exact number. If you've rounded it off at that stage, you might get a slightly different answer here. But mine came out as 98.9583 reoccurring. And if we round that to just 1 decimal place, that's going to get us 99.0. Need to remember units. If we've used our equation properly, then this mass will be in grams. So 99.0 grams. So you must include your units at the end. You may be out by 0.1 or 0.2, depending on if you've rounded off your answer or so on, but that will be taken into consideration in your exam. So you can see there's a little bit more work with these types of calculations, but the only extra bit of work is that you're calculating 2 numbers of moles of each of your reactants, but also you need to remember to divide by the balancing number ratio, and also to take that into consideration when you're transferring over your number of moles. So make sure you've got that example written in, and then we'll do one more example together. So turn over when you're ready to page 24, and we're going to look at worked example 2 together. We'll try and do this a little quicker. It might be worthwhile you just watching me work through this and then filling it in afterwards, just so that you can keep a track of what we're doing, because there's a lot to take in with these calculations. So worked example 2 says, what mass of aluminium chloride is formed from the reaction of 25 grams of aluminium and 90 grams of chlorine? So again, you can see that we've been given 2 masses of our reactants. We've been given 25 grams of aluminium and 90 grams of chlorine. And the likelihood is these haven't been mixed in the exact ratios. So we need to determine which we have less of. And we have less by mass of aluminium, but we may not have less by number of moles. And that's what we have to work out first of all. So, as we did before, let's write down the information that we have underneath our equation. So we've been told that we have 25 grams of aluminium, so I'm going to write that underneath Al, and I have 90 grams of chlorine. We also write a question mark underneath what we're trying to work out, and we're told we're asked in the question what mass of aluminium chloride is formed. So I'm going to put a question mark underneath that. What we also do at this stage to make our life a bit easier is to write down the RFM values. So we can see the RFM of aluminium is 27, the RFM of chlorine is 71, and the RFM of aluminium chloride is 133.5. And you don't need to write down the RFM values that you'll be using, but in this case we'll be using all 3 RFMs, because you can see we've got a mass underneath aluminium, a mass underneath chlorine, and a question mark underneath aluminium chloride. So step number 2 then was to calculate the number of moles of each of our reactants. So let's start with aluminium first of all, remembering that key equation, N equals mass over RFM. Our mass is 25, our RFM is 27. Put that into your calculator. And what you should see on your calculator is 0.9 with a reoccurring symbol above it, 2 and then 5 with a reoccurring symbol over it. What that actually means is that it repeats between 9 and 5. So essentially you have here 0.925, 925, 925 and so on. If you press your S to D button, you'll see that coming up again. You'll see the full number written out. So let's just, for now, we can write down 0.9259. Okay, now step number 3 was to divide by the stoichiometry or the balancing number, okay, and you'll see in this case it does make a difference. So the balancing number in front of my aluminium is 2. So at this stage in my calculation, before I go any further, before I forget essentially, is I'm going to divide by 2. Now rather than retype that number into your calculator, just leave it in your calculator, literally press divide by 2 and then press your equal sign, and that will divide your previous answer by 2. It'll just get you a more accurate number. And again, what you've got here is 0.46 with a reoccurring, then 2, then 9 with a reoccurring symbol. So again, press your S to D button again, and you should see that your answer is 0.46296. We'll round it off at that stage. Okay. So I've worked out essentially my effective number of moles of aluminium, taking into consideration that I need a ratio of 2 of them according to the balancing number ratio. And this is a bit like our pack lunch where we needed 2 oranges. Here we need 2 moles of aluminium to form our product. What we need to do now is do exactly the same thing but for chlorine. So again, we need to work out our number of moles by doing N equals mass over RFM. Our mass is 90, our RFM is 71. Put that into your calculator and you get a number of moles of 1.2676 moles. What do I need to do now? Step number 3 says I need to divide by the balancing number ratio. So essentially here I'm going to divide by 3, and it's really important that you remember to do this each time for these examples. So I'm dividing by 3, and again, if you just put that into your calculator, divided by 3, it'll get you a more accurate number. If we divide by 3, and on our calculator we see that we get 0.4225 moles. And that's taking into consideration that I need a ratio of 3 moles of chlorine, a ratio of 2 moles of aluminium to 3 moles of chlorine. So it's at this stage that I decide which is my limiting reactant, which is step number 4. So with aluminium, I have 0.46296 moles, and for chlorine, I have 0.4225 moles. So this time, our limiting reactant is chlorine. And can you see how we can only determine that after we've divided by the balancing number? Because let's have a look at what values we did have. Before we divided by our balancing number, we had a number of moles of aluminium as 0.925. And we had a number of moles of chlorine of 1.2676. So if we had decided the limiting reactant at this stage, we actually would have said that aluminium was our limiting reactant. But when we've taken into consideration our balancing number ratio, again a bit like our oranges in our pack lunch, then we see that actually we have less of chlorine overall. So our limiting reactant is chlorine, and we go from here. We bring this number of moles over to our aluminium chloride because it's chlorine that's going to stop our reaction from going any further. Once all of that is used up, then there will be no more chlorine for the aluminium to react with, and the reaction will stop. So that determines the maximum mass of product that I have. Now, it's at this stage that we need to be careful. We need to take into consideration our balancing number ratio. You can see here that our ratio is 3 to 2, which means divide by 3 and times by 2. But we have already divided by 3 at this stage. That was step number 3. We've already divided by 3. So all we need to do is multiply by 2. So be really careful. That's different than our reacting mass calculations. Because we've already done the divide by 3 stage, we just need to multiply by 2. So you multiply by 2, and again, if you've kept that number in your calculator, you'll get a slightly more accurate number here of 0.84507. So that's the number of moles of aluminium chloride that we could potentially form. What was I asked to do in the question though? I was asked to calculate what mass of aluminium chloride is formed. So I need to convert this back to mass. Mass equals N times RFM. Remembering your key equations. Our number of moles is 0.84507. Our RFM is 133.5. Put that into your calculator and you should get an answer to 1 decimal place of 112.8 grams. Remember, you need to include your units. So it might be worthwhile highlighting that times by 2 and just writing yourself a little note that you have already divided by 3. So we just multiply by the number in front of what we're going to. Okay, so it probably seems right now like there is a lot going on in these calculations, and this is as hard as it gets in terms of these calculations, and even the moles chemistry that we do in year 12 is probably less difficult than this. So what we're going to do now is take some time for you to do some examples yourself of these. And when you're carrying out these calculations, I just want you to think through these steps. I want you to take it slowly, and hopefully you'll find that these are not too bad and that you do exactly the same thing each time. But it's worth taking it slowly at the start and getting it right, and then you'll get into good habits. If you do it too quickly, you might forget about dividing by your balancing number, just multiplying by it when you're taking it over rather than doing your whole ratio again, things like that. Just be really, really careful with that. So as you can see, go through your steps, write the information underneath your equation, work out the number of moles of both of your reactants, divide by your balancing number ratio to determine your limiting reactant, and bring over the smaller number of moles to your product. So at the bottom of page 24 and then on page 25 as well, you have a total of 6 questions to complete now, and they are all these limiting reactant examples. So they will all involve determining which is the limiting reactant by calculating the number of moles of both of your reactants. So it's all the type of examples that we've been doing in this video. I'd like you to complete these in your blue book. I would like you to write out your equation and do all your working out underneath the equation as we've done in our worked example. So in your blue books, you should be writing out your equation and doing your working out underneath. So this is what the start of your working out might look like for question 1. So you can see I've written out the equation, I've written out the information that I've been given in the question below the relevant parts of the equation, and I've written my RFM values of the components I'm going to be using, the reactants and products in the equation that I will be using in my calculation. And what you should also do then is check that your final answer matches the one given to you in your notes. So for each question, just as I did before, I've given you the very final answer, but obviously it's not enough for you to just write that answer down. I've put those there so that you know that you're on the right track. So if you've done it correctly, your answer should match that. If you haven't, if your answer doesn't match that, you've done something wrong at some stage. And again, your most common mistakes will be things like you've used the wrong RFM value, or you have forgotten to divide by your balancing number before determining your limiting reactant, or you've forgotten to multiply by your balancing number when you're bringing it over to your product. So those would be your key mistakes. So what I'm going to do for these questions, just because they're that little bit more tricky, and I don't want you to do number one, get it wrong, and then not understand where you're going wrong. What I'd like you to do now is pause the video. Try this yourself, as if you were just starting these questions from scratch yourself. In your blue book, do the whole calculation, and if you're not getting the right answer, then watch the video to check, to maybe determine where you're going wrong. So I'm going to do this first example now, but I would like you to pause the video and do it yourself first, and then check to see if you haven't got the right answer, then you can check the video to see how where you may have gone wrong, and do work through it with your own example in front of you and try and identify where you have gone wrong, and make sure that you don't make that same mistake again in the future examples. And after that, then it will be a case of completing all 6 of those questions before moving on to the last section of this topic. Okay, so here is question 1, and again, make sure you've done this yourself before going on with this video and watching it. Make sure you've had a go yourself. So you can see here what I've done is I've written out my equation first of all, and when you're doing these you should try and spread out that equation across your page as widely as you can, making sure you fit it all on one line but spreading it out so that you have enough room to work underneath your particular reactants or products. So the first part of our process here is to write the information we know underneath the equation. So we're told that we have 16 grams of iron oxide, and they were placed in a crucible with 12 grams of carbon. So we've been given the mass of 2 reactants, so we know this, we need to do it the limiting reactant way. So I've got 16 grams of iron oxide and 12 grams of carbon. What are we being asked to work out? It says calculate the mass of iron formed. So I'm putting my question mark underneath the formula for iron. Let me write down the RFMs that I'm going to need to use, and you're given those in the question as well. That your RFM of iron oxide is 160, your RFM of carbon is 12, and your RFM of iron is 56. You're given the RFM of carbon dioxide as well, but we won't be using that in this calculation. So what you start by doing is pick one of your reactants, work out the number of moles, and then remember to divide by your balancing number. So we're using our equation, N equals mass over RFM. The mass is 16 grams, your RFM is 160. And so that's 0.1 moles. What we need to do is, remember step 3 of this process is to divide by the balancing number ratio. So the balancing number is 2, so I'm dividing by 2 in this case. 0.1 divided by 2 is 0.05 moles. You're better to do that at that stage so that you don't forget to do that. Now what we need to do is the same process for carbon. So work out your number of moles, N equals mass over RFM. Your mass is 12, your RFM is 12, and so that gives me 1 mole. Again, I need to divide by my balancing number, and we'll highlight that in blue. So this time I'm dividing by 3. That gives me 0.333 reoccurring moles. So which do I have less of? I have less of my iron oxide, 0.05 moles. That is my limiting reactant. Once that is all used up, then the reaction will stop. So that determines how much iron I can form. So I'm bringing that over to my iron now. But what we need to remember, yes, the ratio is 2 to 4. I'll write that up here. But remember, that means divide by 2 times by 4. But we have already done the divide by 2 stage previously. So all I need to do at this stage is multiply by 4. So remember, you're essentially just multiplying by the number in front of where you're going to. And that's particular to these limiting reactant examples because we've already done the dividing by stage essentially with our ratio. So now what we want to do is multiply my number of moles of iron oxide by 4, and that gives me 0.2 moles of iron that I will form. So 0.05 times by 4 is 0.2. Then we need to work out our mass of iron. So we use the equation mass equals N times RFM. Our number of moles is 0.2, our RFM is 56, and that gives me a mass of 11.2, and our units of mass are grams. So hopefully that helps if you did make a mistake. Try and identify where your mistake is and make sure you don't make that mistake in future examples. So again, I want you to now complete questions 2 to 6. Writing out your equation, doing all your working out underneath. Don't take any shortcuts, particularly not at this stage. And if any of your answers don't match up to the final answer, check through, see if you can identify yourself where you've gone wrong, or if you're really stuck, then you can email me. And that takes us to the end of our limiting reactant calculations. The next video will be on percentage yield, and that will finish off this topic.